Almost every engineering organization has AI coding tools now. Over half of developers rely on AI daily. Almost none of them ship software meaningfully faster. And it isn't because the tools don't work.
There's a ton of investment, good adoption statistics, and positive response from developers. And yet, at the macro level, delivery speed, predictability, overall engineering outcomes, the shift is far less visible, let alone the ROI.
This framework is what survived over 150 engagements in the last 2 years. How AI changes the lifecycle, where it doesn't help, what it costs to scale without guardrails, and how to tell the difference from your own delivery data rather than someone's benchmark. There's a difference between sporadic tool adoption and a cohesive framework for AI in the SDLC.
You give a tool to 300 engineers and you hope that they will figure it out. A few high performance reach like around 30% boost, but the rest of the team stagnates because you don't scale performance by handing out licenses to the developers. You need to rethink how the entire team works.
When adoption stays individual, the gains stay individual. Most conversations about AI and software development default to coding assistants, tools that auto-complete lines, suggest functions, and speed up the mechanical parts of writing code. That's a narrow slice of what AI in the software development lifecycle actually covers.
Let's take an example of legacy code refactoring or unit test generation, or even the code to documentation, vice versa. So you can get 30 to 50% of boost for individuals. But when you factor in the entire SDLC and the team performance, the code reviews, the rework, and the learning curve, you get a sustained around 10 to 20%.
The useful way to think about it isn't a list of tools. It's a question of where AI sits relative to your process. 3 levels, and much of the confusion in this space comes from people at different levels using the same word. Level 1, assistance. Copilot style tools. The developer is still the author. Every suggestion gets accepted or rejected by hand. Individual tasks get faster. How software moves through review, testing, and release doesn't change. Level 2, augmentation. AI moves inside the workflow instead of sitting next to it. This is where the numbers a CTO reports upward start moving. Cycle time, defect escape rate, release frequency. Level 3, Agentic. Agents don't wait for a prompt. They plan, execute multi-step work, check the result, and correct themselves. Engineering judgment doesn't disappear. It moves to reviewing agent output, setting the boundaries of autonomy, and owning the decisions that carry real risk.
In AI-assisted workflows, you have an engineer, he starts coding, he reaches the bottleneck, he then prompts the LLM for help, and then he is the driver of the entire coding practice. The AI native workflow flips that picture. So AI connects to your Jira, gets your Jira ticket, starts to code the boilerplate, and then creates your unit test, and you just verifying now whatever it is created. So you become more like a reviewer and an editor. And then when you systematize that for the entire SDLC, you get that boost, and this gain becomes sustainable.
Held against your own lifecycle, the 3 levels become a diagnostic. Walk through each phase and ask which level describes it honestly. The phases still at level 1 are where AI has been bought but not integrated, and that gap is usually where the missing ROI sits. 6 phases. For each, what AI does there and what it costs to get it. Requirements is where projects quietly get expensive. AI's advantage here is reading volume early. It goes through support tickets and customer conversations and surfaces what users are actually hitting. Problems that rarely reach a requirements workshop, because the people in that room aren't the people filing tickets. Then it checks the spec against itself. Contradictions. Stories with no acceptance criteria. Requirements loose enough that an engineer has to guess. The technique is called spec-driven development. Business writes what they want in plain English. AI turns that into a behavioral spec. A document that says exactly what the system should do, step by step, including what counts as done and what happens when it fails. Engineering builds from that, and the finished work gets checked back against the same document. One caveat, AI-generated requirements are only as good as what you feed them. If stakeholders disagree, AI surfaces the disagreement faster, which is useful. That's still a conversation between 2 people who want different things. Architecture decisions are the cheapest thing to change and the most expensive thing to get wrong. Design review has always run on intuition. You put a diagram on a screen, and a room of experienced people say whether it feels right. What AI changes is the economics of that review. You can generate the architecture from the requirements and then actually run it. Push simulated traffic through it, break a service on purpose, and see what else goes down with it. Check how your queries hold up at the load you're expecting, not the load you have today. And you can ask for options. Same requirements, but optimized for cost, or for latency, or for compliance, or for whoever's on call at 3 in the morning. The return is slower and harder to attribute than in coding, but the arithmetic holds. A structural flaw caught at design costs an afternoon. Caught 6 months in, it costs a quarter. Coding is where AI is most visible and most measured. It may also be where its contribution is most easily overstated. Here's what a developer's work cycle looks like. Work out what's being asked, find where it belongs, write it, watch it break, fix it, test, tidy, open the PR, then wait for a reviewer, rework, wait again, merge. 10 steps, and only one is writing code. Orientation at the front and waiting at the back take far more elapsed time than typing ever did. The figure quoted most often for AI's effect on coding is around 30%, and it's worth holding loosely. Large studies put it anywhere from 16 to 55, and some have found developers got slower. But 30% off one of the shortest stretches of the journey is why a team can adopt Copilot, feel faster, and see no movement in cycle time. Both can be true at once. Worth noting alongside it, these tools lean toward writing new code rather than reworking what's there. GitClear's commit analysis shows refactoring falling steadily since 2020, and copy-pasted code overtook it for the first time in 2024. Adding refactoring rate to what you already track is worth considering, because duplication is the one form of AI-induced debt that won't appear in cycle time or defect escape rate until it's expensive. A quieter effect, and possibly a larger one, getting an engineer to the point where they understand an unfamiliar part of the system used to mean interrupting whoever wrote it. What does this module do? What calls it? Why is this here? That gain is hard to capture in a productivity study because what it produces is an absence. 20 minutes a developer didn't spend reading someone else's code, and an interruption a colleague didn't absorb. Test coverage benefits similarly. When writing tests costs very little, the ones that tend to get skipped as a sprint closes are more likely to get written. The saving isn't in authoring time. It's in the defects that don't reach production later. The shift that shows up most reliably in delivery data happens further along, at review. AI now reads the diff before the reviewer does, flagging security exposure, logic that doesn't do what the author intended, standards violations, performance concerns, dependency conflicts. What changes is how a reviewer spends their attention. Less of it goes on formatting, more on the two questions AI can't answer. Is this the right design? And does it do what the business asked for? Since waiting and re-reviewing are where the elapsed time sits, that's the change you'll feel.
You trust your engineers, you pair them in the peer-to-peer code review sessions, and they help each other to go through the hallucination cycles. So that's a certain trade-off of using AI. So you don't normally verify the quality of the output. With your colleague, you can, right? So this is the mandate for scaling. This is the pure mechanic that works inside of the teams.
Traditional test coverage tends to reflect what was front of mind when the tests were written, usually close to a deadline. AI moves the starting point. Tests get generated from requirements before anyone implements anything, and coverage gets measured against the spec rather than lines of code. Line coverage tells you which code ran. Spec coverage tells you which requirements you've proven. Only one of those means anything to the person who asked for the feature. It's also what catches what tends to get skipped. Negative paths, empty inputs, dropped connections. On one recent engagement, a US SaaS company with around 300 engineers using Java and React.
Within 3 months, test coverage on legacy modules jumped from 40% to 75% without even impacting feature delivery.
There's one failure mode worth naming specifically. When AI generates both the implementation and its test cases, the tests inherit the same assumptions as the code. Test pass, code ships, requirement goes unmet. And an honest note, because this is where overclaiming tends to happen. If you already have mature CI/CD and strong test automation, testing will give you the smallest release cadence gain of any phase here. Release management is still the most manual part of the lifecycle. Scripted pipelines, manual gates, and deploy windows scheduled around risk tolerance rather than readiness. What AI changes is what a deployment decision is based on. Your pipeline history knows things no single build log shows. Which stages drag, which ones fail on Fridays. What a bad build looks like before it finishes failing. That's pattern recognition, and it's what this technology is good at. 2 examples. Reorder tests by how likely they are to fail. Same coverage, but a broken build tells you in 4 minutes instead of 40. And canary releases that tune themselves. The rollout widens while error rates stay flat and stops the moment they don't. Then score every deploy for risk, so the ones needing another set of eyes get flagged and the routine ones go through. The phase most organizations underinvest in, and consistently where AI returns the most. The mechanism is unglamorous. Faster detection, faster diagnosis, faster resolution. It compounds because AI reads every log and metric across every service continuously, which is precisely the job humans are worst at. The valuable part is the leading indicators. Memory creeping up over 4 days. Latency drifting 30 milliseconds a week. An error rate inside tolerance, but moving in one direction. From there, it's a chain. root cause traced back to the change that caused it, tickets routed with the last fix attached, and monitoring agents that find the cause, write the patch, and put it in front of a human. Measure before you change anything. Before introducing AI, establish a baseline, track metrics like cycle time, change failure rate, pull requests per engineer, and defect escape rate. This gives you a clear way to measure whether AI is actually improving delivery. At the same time, look at where work slows down, where handoffs create delays, and where defects typically originate.
We do this experience in a measured way. We tracked at least 4 key metrics on every single account, and we basically quantify the results for the business people, even the money.
Your engineering foundation matters too. AI works best when repositories, tests, documentation, and telemetry are current and connected. Otherwise, weak inputs can quickly limit the value you get from AI.
And there is something about the consultancy that you come in and people are sharing some of the bottlenecks quite openly because they trust that you can help them to change that. That's why it actually works even better in this environment. So when somebody externally comes and gives you the hope that AI would actually bring those changes to you and gains as well.
There is no single best place to introduce AI. Start with a bottleneck that has the biggest impact on your team. If requirements cause rework, start there. If code reviews are slowing delivery, introduce AI-assisted review. If defects reach production, focus on QA. If deployments take too long, look at CI/CD. The goal is simple. Apply AI where it can remove measurable friction, rather than introducing it across the entire lifecycle at once. Next, test the approach on real production work. Keep the pilot focused. One team, one SDLC stage, and one workflow. Compare the results against your baseline and document what changed. A short pilot can show whether the approach has real value before you commit to broader adoption. What matters is not whether developers like the tool, but whether it improves metrics such as delivery speed, quality, or engineering effort. That documented workflow then becomes the starting point for scaling AI across more teams. Governance should be part of the rollout from the beginning. Define which AI tools are approved, what data and code they can access, and how much autonomy they have. Apply the same CI, security, and quality gates to AI-generated code as you would to any other code. You also need clear rules for where human review remains mandatory and a consistent way to measure impact as adoption grows. This becomes especially important when moving from a successful prototype into production. Tests, security reviews, documentation, and approval processes still need to be in place. So the approach is straightforward. Measure first. Start with the biggest bottleneck. Prove the value on a small scale. Then, put the right guardrails in place before expanding.
Before we wrap, I feel like a word of wisdom would make sense. So, Yaroslav, what's the one thing you see engineering leaders, technology leaders get wrong when trying to scale AI independently?
Treat AI like any major change. It's a management challenge after all, not just a matter of tooling. If we fail to keep humans in the loop, foster team collaboration, and actively drive adoption, our expensive AI will simply generate technical debt, only much faster.
Everything here came out of doing it. Over 150 engagements in the last 2 years. The way we work is co-implement, then transfer. NIX engineers embed with your teams and build the workflows on your actual code base in live production work. Then, we train your people to run them without us.
We came up with our structured adoption, which we call APEX. It stands for Assess, Pilot, Expand, and Excel. So we first assess the baseline, where the company is, what are the short, quick wins, and we try to quantify that. Then we transition into the piloting stage, where we take the most impactful 3 to 4 workflows, and we embed them and pilot them and show that they actually work with production-grade code. Afterwards, we expand, and not just for the initial teammates, but we train additional AI champions and scale this beyond other teams. And finally, we reached the Excel stage, where the teams are basically integrating the advanced AI workflows into their delivery pipeline across SDLC with agents and other elements.
And the return isn't only in delivery speed.
For instance, on the last project that we did for around 400 engineers, we gained for the management around 1.5 to 2 million of savings for the change management.
If your teams are using AI tools but your delivery numbers haven't moved, the place to start is a baseline assessment. We map current usage against your actual delivery data, show where adoption is generating value and where it isn't, and give you a roadmap for what comes next.